seen the demonstration through an example, how the efficiency, in fact, the voltage regulation, the efficiency enhances in the auto transformer especially, and especially the kVA rating of the auto transformer, it increases, right, more when the same size of the transformer or same number of windings we considered as compared to the two winding transformer. So therefore auto transformer has an advantage of using it in the interconnecting substations where we have a very long line, long transmission line, and we need an intermediate substation for the voltage regulation purpose. Under that condition, generally we use the interconnecting auto transformers. And also auto transformers are very useful when it is used as variac, when we need a variable voltage, right? Please mute yourself. So when you need a variable voltage output for experimental purpose, these auto transformers are very useful. Okay. So already we covered, and today in this lecture we'll cover the three-phase transformers. So till now, whatever we discussed, it is all of single phase nature. We considered that the transformer is a single phase transformer having two windings, or the two windings connected in series, which is called auto transformer. Okay, so we'll move with three-phase transformer. Generally, whatever we see, the power transformers at the distribution level or interconnecting transformer, or you go to the generating substations where you'll find the step-up transformers. They're all in fact three-phase transformers. But it is always better to, when we're doing the analysis, it is always better to do the single-phase analysis. That means when the transformer, three-phase transformer is there, if we can represent that through a single-phase equivalent circuit, then it is better. Through that way we can analyze the transformer very easily, right? So now in this lecture we will also see how we can represent the three-phase transformers through their single-phase equivalent circuit, and so that the analysis becomes easier. Okay. So now the three-phase transformers, in previous days, when in fact around maybe in 40s and 50s, these three-phase transformers are designed considering the single-phase transformers. Like if we'll consider three single-phase transformers and you connect it in various fashions. So already we know the various fashions, like we can connect star star or star delta, delta star, right? Delta star or delta delta. We can connect three single phase transformers in various ways, right? Either star star, star delta, delta star, or delta delta. We can connect it in various fashion. Just we need to connect the winding terminals in this fashion, right? So, and in that way we'll do our analysis. And also three-phase transformers in the modern transformer design has made the way we can have a three core, or we can have a single transformer with three cores on which the windings are placed, right? So in case of single phase transformer, we have seen there are two types of transformer. One was your core type transformer. So one was your core type transformer, and other one is your cell type transformer. Already we have discussed this, right? So the difference is the core, in case of core type transformer, the core, in fact, the winding is on the core, right? That means the windings are in fact engaging the core, and in case of cell type transformer, the core is in fact encirculating the winding, right? So this is the difference we have seen. This is a core type transformer. You can see this is a three-phase core type transformer, right? So the three-phase windings are connected. You can see each limb we have phase A, phase B, and phase C winding. So each of the phase has primary windings. Phase A has primary winding, phase B has primary winding, and phase C has primary. Primary winding mean this is connected to the source side. This can also be primary side when it is connected to source. But for this illustration, I am showing A1, B1, and C1 are the primary windings, and A2, B2, C2 are the secondary windings of each of the phases A, B, and C respectively, right? So now this is your core type transformer, right? So now if we'll see the cell type transformer, the structure is like this. You can see here in the middle limb, the windings are connected, right? The windings are owned on the middle limb, right? So where this A1, B1, and C1, they form the primary winding of the three phases A, B, and C, right? And similarly, A2, B2, and C2, they form the secondary windings of the phases A, B, and C respectively, right? So, but these windings are owned in the middle limb of the core, right? The core is encirculating the winding, in fact, right? So here, so what is the advantage of doing this uh, three-phase transformer on a single core instead of connecting the three single-phase transformer? There are certain advantages because when we use the three single-phase transformer, it occupies a lot of space, and also the volume, the cost becomes very high. Okay, because we are having three separate transformers, right? Separate insulation, separate winding arrangement, everything. So the cost increases and the space requirement increases. The size also increases. But here, when we do in a single core, when we do this three-phase transformer, whether it is core type or cell type, in fact, the size reduces, the cost reduces, and the requirement of the space for installing these transformers, that also decreases, right? Okay, this is how it is advantageous economically, right? And also the space requirement also reduces. So now if we'll see different connections of the three-phase transformers. So as per the requirement, we connect these three separate windings of each of the phases in a different way in both primary and secondary sides, right? So now we can see, already I told you there may be four possible combinations or possible connections of the three-phase transformer. One is YY, delta delta, and delta Y, and your Y delta, right? That means star star means your primary is star, secondary is star. Delta delta means primary is delta, secondary is delta. Delta star means your primary is delta and secondary is star. And star delta means star is primary side is star and secondary side is delta. So with a particular application we use, like most of the time in the distribution, for the distribution application, we use delta star combination. And for your transmission application, like when the bulk power is transmitted, we use star star combination because at that point neutral is very essential, right? So based on the application, we use different connections, right? So now whatever you are seeing in this figure, it is a star star connection. We can see there is a neutral point here, common neutral point, where each of the undotted terminal is connected at this star point, at the end neutral point. Similarly here also, each of the undotted terminal, right, they are connected to the neutral point here. So this is a star star connection, and if we'll draw the phasor diagram for this, so if we'll just plot the phasor diagram, suppose I want to draw the phasor diagram for phase voltage and line voltage. Generally, the three-phase transformers, the nominal voltage ratio generally we measure in terms of line voltage, VLP, right? Or you can say BPL by BSL, right? VPL is your primary side voltage. This is your nominal transformation ratio. Generally, we take the ratio of the line to line voltage. VPL means primary side line voltage divided by secondary side line voltage. Therefore, here always when we represent the nominal voltage, we should represent it through the line voltage, line to line voltage, not the line to phase voltage, right? So here if we'll draw the phasor diagram for star to star connection, so if we'll let us say this is your VAN, that is the phase voltage of phase A, right? For the primary side, let us say, or I'll mark it as 1, VAN1, right? And this will be, if I'll consider the positive sequence, then this will be VVN1, this will be your VCN1, right? Okay. So these are all phase voltages of a positive sequence connection, right? They're all 120 degree apart from each other. Now, if I'll draw the line voltage, so if I'll draw the line voltage VAB, so VAB1 will be in this direction, right? Sorry, this will be VNB and VVN will be here, VAB1, right? Okay. Similarly, your VAB1 is leading 30 degree by VAN1, right? Similarly, your VBC will be BC will be in this direction, which is leading VBC1, which is leading 30 degree to VVN1, right? And similarly, your VCN or VCA1 will be VCA1 will be here in this direction, right? VCA1. So now this is your primary side voltage. Now if we'll draw the secondary side voltage, it will be almost same, right? VAN2, then VVN2, then this is your VCN2, and this is your VAB2, this is your VB2, sorry, VBC2, this is your VCA2. Okay, so now if we'll see the phase difference between the primary line voltage to secondary line voltage, what is the phase difference? The phase difference will be 0 degree, right? So therefore we call it 0 degree connection, star connection with zero phase difference between the primary voltage and the secondary voltage, right? Similarly, if we'll go for a delta delta connection, so if we'll go for a delta delta connection, now let me erase this. So for delta delta connection, if I'll plot the same, right? So for a delta connection, we know the phase voltage is equal to the line voltage, right? So phase voltage is equal to the line voltage. So therefore I can, if I'll plot VAB, VAB1, VBC1, VC1, and in the secondary side also it will look like same, VAB2, say in the same phase, VBC2, and this is your VCA2. So therefore here also the phase difference between the line voltages of the primary and secondary side will be how much? It will be 0 degree, right? So therefore it is also 0 degree connection. We call it 0 degree connection with delta delta fashion, right? So the connection is in delta delta, but the phase difference is 0 degree, right? So this is how we represent. Now if we'll go for star delta connection, this is a star delta connection, right? If we'll see, this is a star delta connection because your primary side in the star connection, this is your neutral point, and this is in the delta connection, your secondary side, right? Now for this case, if we'll plot the phasor diagram, how it will look like for line voltage, if we'll find the line voltage for the primary side for the positive sequence condition, this is your VN1, This is your VAV1, right? This is VVN1. This is your VCN1, right? And here will be VBC1. Here is your VCA1, right? Okay. So now these are the line voltages VAB1, VBC1, and VC1, VCA1. Now if I'll draw the secondary side voltages, it will be in the delta connection. So therefore, in the because the phase voltage here in the primary side will be equal to the in phase with the line voltage of the delta side, right? So therefore, the phase voltage here is VAN1, which is in phase with the line voltage of the secondary side, right? VAB2, and the phase voltage in the phase B is in phase with the line voltage with the BC, right? In the secondary side, right? Here VCA2. Now if we'll see the phase difference between the line voltage of the star side, that is primary side, and the secondary side, then what is the phase difference? The phase difference is here it is VAB1, here it is VAB2. The phase difference is 30 degree, right? That means your primary side voltage, your primary side nominal voltage is leading the secondary side nominal voltage by 30 degree. So therefore we call it 30 degree connection, right? 30 degree connection star delta. Star delta connection is 30 degree connection, right? Similarly, if we'll see here, this is your connection for delta star, right? So here is your star point. So this is your delta star connection where your primary windings are connected in delta and secondary windings are connected in star, right? So here if we'll draw the phasor diagram, what will happen? So we know the phase voltage of the secondary side will be in phase with the line voltage of the primary side, right? Okay. So therefore, if we'll draw the secondary side voltage, this is VAN1, this is VBN1, sorry, VN2, it is 2, it is secondary side. VBN2, this is your VCN2, and this is VAB2, VBC2, this is your VCA2, right? Okay. So now if we'll draw the primary side voltages, primary side voltage will be here. It will be VAN1, or I can say VAB1, right? Because the phase voltage is equal to the line voltage. So this will be your VBC1, this will be your VCA1, right? So now if we'll see the phase difference between the line voltage and the phase voltage, right? We can see here if we'll compare here in the previous case, in the case of star delta, what is happening? Your primary side line voltage is leading to the secondary side line voltage. But here in case of delta star, your primary side line voltage is lagging the secondary side line voltage. So here it is called 30 degree lag, right? Your secondary voltage is lagging. So therefore 30 degree lag connection, Y delta connection, right? For delta Y connection, it is 30 degree lead condition, right? 30 degree lead connection. So this is 30 degree lead connection because your secondary side line voltage is leading your primary side line voltage. Here, your secondary side line voltage is lagging the primary side line voltage. Therefore, here it is 30 degree lagging connection, right? Lag connection. Here it is 30 degree lead connection. Okay. So this is the difference. And obviously the ratio, the nominal ratio also changes with respect to the magnitude, right? So your nominal ratio, as I told, is nothing but the line voltage of the primary side divided by the line voltage of the secondary side. So therefore, if we'll take the line voltage for these cases, it will be different, right? So therefore, your nominal ratio also changes, right? So we'll see this through an illustrative example. in the future slides. Now it is coming. It is example. So you can see here. So a three-phase transformer is assembled by connecting three single-phase transformer, and the each of the single-phase transformer is rated at 720 volt ampere, 360 by 120 volt, right? The constants for each of the transformers are RH equal to 18.9 ohm, XH, these are the equivalent circuit parameter, XH equal to 21.6 ohm, RL equal to 2.1 ohm, XL equal to 2.4 ohm, RCH equal to 8.64 kilo ohm, and XMH equal to 6.84 kilo ohm. For each of the four configurations, determine the nominal voltage. Nominal voltage means we need to find the line to line voltage in each side, right? Primary side and secondary side. Power ratings of the three-phase transformer. We know the single-phase transformer power rating. We need to find the three-phase transformer power rating. Draw the winding arrangements and per phase equivalent circuit for each configuration. Per phase equivalent circuit, right? Okay, because every analysis will do through this per phase equivalent circuit, right? So here the assumption is that the load is balanced, everything is the transformer is operating under balanced condition, right? Okay, so now we have a single phase transformer, three single phase transformers, right? They will be connected in, this is a single phase transformer. Like this, we have three transformers which will be connected in the three phase fashion, right? Okay, and each of the transformer is rated at 720 VA, right? And the voltage ratio is 360 by 120, and the parameters are given. The equivalent circuit parameters are given here. RH equal to 18.9 and other parameters are given similarly. So using these parameters, we have to represent the per phase equivalent circuit, and we need to find the nominal voltages, power ratings, right? All these things. So first coming to the power rating. So what will be the power rating of the three-phase transformer? If single-phase transformer is having 720 VA, then three single-phase transformers are connected together. So if we'll use the per phase voltage and current relation, then for a three-phase transformer, it becomes 3 VPH IPH, right? So that will give me 3 into 720 VA, right? So, or else for a line, if we'll use the line voltages, you can write it root 3 VL IL for delta star connection, whatever. That will lead to, in fact, if we'll convert this to per phase quantity, it will become 3 into VPH IPH. So for each of the three phase transformer, like we have four combinations, four configurations, YY star star, YY delta delta star delta, then delta star. For four configurations, for each of the configuration, we have the rating of 3 VPH IPH. That means 3 into 720 VA. So for each of the configuration, your transformer rating will remain same. That is 3 into 720 VA, right? So now let us proceed. So this is your three-phase transformer rating. That is nothing but 3 into 720 VA, 2160 VA. Okay, that is equal to 2.16 kVA. Okay. So now we'll consider now the YY connection. Then each of the connection configuration we'll consider. For each configuration, we'll have to find the voltage, nominal voltages. Then we have to show the winding arrangements and the per phase equivalent circuit. Okay, so let us first consider YY connection. For YY connection, your line voltage obviously will become, because these are all phase voltages, right? 360 and 120. So they are now connected in the star fashion, star fashion. So your line voltage in the primary side will become root 3 times 360. That will be nothing but 623.54 volt. And in the secondary side, your line voltage will become root 3 times 120. That will become 207.85. So now your just by approximation these voltages can be made 624 is to 208. Okay. So now your transformer, as for the star star connection, your transformer rating became 2.16 kVA. Nominal voltages became 624 is to 208 volt, and this is a star star connection, right? Okay. So now we have to, if we'll see the winding arrangement, it is very simple, right? Just we need to connect all the phase windings in star fashion, right? So these phase windings we can see they're rated at 360, 361, minus 120, 360, 120, right? And these are the line voltages given. And similarly at the secondary side we have, right, this connection. This is also star star connection. Now if we'll represent the per phase equivalent circuit, it is nothing but it is the representation of the, because if we'll see the per phase representation, your per phase voltage will be 360. So already given for 360, 120, we have these parameters. And using these parameters, we can now draw this equivalent circuit, per phase equivalent circuit for star star connection, right? Now already we know this is your high voltage side, the primary side, right? So therefore the high voltage parameters are represented here. 18.9 ohm is RH, 21.6 ohm is your XH, then your XMH is your 6.84 kilo ohm, right? And RCH is your 8.64 kilo ohm. Similarly, your RL and XL, RL is 2.1 ohm and XL is your XL is 2.4 ohm, right? So this is very simple representation for star star connection. Now let us see for delta delta connection. So for delta delta connection, how we'll find the ratings of the transformer, then the nominal voltages across primary and secondary, then we'll find the winding arrangement and the power phase equivalent. So now if we'll see the rating, the transformer rating will remain same. It will be 3 into 720, right? It is 2.16 kVA. So it will remain same. And the winding arrangement if we'll make, so all the phase windings will be connected in the delta fashion, we can see here, right? And for each of the winding they are connected in delta fashion. If we'll connect the voltage sources, now your voltage will have angle of like this 360 30 degree, because this will be leading voltage VAB1, right? VAB1 will lead by 30 degree to VA1, right? Already we have seen this. So similarly in the secondary side also the line voltage will lead, right? VAB2 will lead 30 degree to VAN2. So these are all leading, right? Now if we'll draw the here you can see the nominal voltages. The nominal voltages across primary will be 360 volt, because phase voltage and line voltage magnitudes they will same. So your V1L, the primary side nominal voltage will become 360 volt, and your secondary side nominal voltage will become 120 volt, right? And the transformer rating is like this. It will be 2.16 kVA, 360 is to 120 volt, your nominal ratio, and this is your delta delta connection, right? Now if we'll convert it back to the star connection, right? Because we need to find the per phase equivalent circuit, so therefore we are converting it to the star connection. That means star equivalent. So if we'll convert this to star equivalent, your per phase voltage will become 120 by root 3, right? As we can see here in the secondary side, and in the primary side it will become 360 by root 3, right? And your angle will become, already I told, VAN1. VAN1 will become 0 degree angle, phase angle 0, and then VB1 will be minus 120, VC1 will be plus 120. Similarly, Here also VAN2 will become phase angle 0 degree, phase angle minus 20, then plus 20 for VBN2 and VCN2 respectively. So now if we'll draw the equivalent circuit, so before we proceed to find the equivalent circuit, we need to find the Z parameters. That Z parameters means that involves that comprised of resistance and reactance. So that we can find, just if I'll take for star connection, it will be VSCY by ISCY, right? Because this will give me the per phase voltages, right? And now it is equal to, so your star, your in case of your star connection, the phase voltages, this is in fact the phase voltage, right? Phase voltage, okay. So the phase voltage will be equal to the delta side. In case of delta connection, it will be the line voltage by root 3, right? So therefore I can say VSC delta by root 3, and your current will become in that case root 3 ISC delta, okay. So therefore it will become 1 by 3 PSC phase voltage by ISC phase voltage. This is your, because in the delta connection your line voltage is equal to phase voltage, so I can write this is phase voltage and phase voltage. So therefore 1 by 3 Z equivalent phase, right? So that means your whatever your Z equivalent in the Y connection will now become, in case of delta connection, it will become 1 by 3 times Z equivalent. That means all the parameters, whatever we are considering in case of star connection, it will now become 1 by 3. That means one third of the phase quantity of the Z equivalent, right? So now if we'll represent the equivalent circuit in both the side, because both side are delta, now your parameters will be divided by 3. Okay. So your RH will be divided by 3. It will become 6.3 ohm, right? And your XH will also divided by 3. It will become 7.2 ohm. Similarly, XL and RL dividing by 3, because this side, secondary side, is also delta connection, right? Similarly, your RCH and XMH, they are also divided by 3. Okay. So now your for delta connection, if we'll represent the per phase equivalent circuit, your equivalent circuit parameters are always divided by 3 from this equation, right? Okay. Now for your star delta connection, this is all delta connection. So for star delta connection, what will happen? For star delta connection, you can see here your line voltage will change, right? Because it is in the star connection, so your line voltage will change. It will become 624, 624, 624, and the phase angle also will change, 30 minus 90 and 150. But in case of delta connection, your phase voltage will remain same as the line voltage, right? 120, 120, 120, and the angular difference will be 0 minus 120, 120, right? So now because we are considering here this as the in phase, so therefore your here the whatever induced EMF will be in the phase voltage, the phase angle will be same. So it will be also 0, and which will be equal to the line voltage in case of delta connection, right? So therefore 120 0 we have represented here. It is 120 minus 120, 120, 120, right? Okay. So now the rating of this transformer will become 2.16 kVA, 624 is to 120, because the line voltage across the star side is 624, and the line voltage across the secondary side is 120. So 624 by 120, it is the star delta connection, right? Okay. So now if we'll see the winding arrangement, already the winding arrangement is almost same, right? Now this is for star equivalent. So the star equivalent of this circuit will be this, right? The primary side it will remain same, and the secondary side will change for phase equivalent circuit. Sorry, the star equivalent of the delta side, it will become 120 by root 3, 120 by root 3, 120 by root 3, and the phase angle obviously we know it will lag, right? Lag by 30 degree, right? Okay. So now if we'll represent the equivalent circuit, power phase equivalent circuit. So power phase equivalent circuit for primary side will remain same because this is now the star connected side. The star connected side means the primary side equivalent parameters will remain same. Whereas the secondary side it will change because the secondary side is delta connected, right? So therefore all the parameters as we have seen in the last slide, all the parameters will be divided by 3. So now it will become 0.8 ohm and zero point 0.7 ohm just by dividing the original single phase parameter by 3 you will get 0.8 ohm and zero point 0.7 ohm. This is for XL and this is for your RL, right? Okay. So now this is the power phase equivalent circuit for star delta connection. Similarly, if we'll consider the delta star connection, for delta star connection, we can see the star side will remain same almost only because in the secondary side it will remain same and in the primary side it will change, right? So primary side the changes are like this. So therefore the nominal voltage ratio will become 360 by 208, right? And here the line voltage is 208 and the rating of the transformer will remain same 2.16 kVA. This is a delta star connection. Now if we'll do star equivalent representation, your primary side will only change but your secondary side will remain same, right? So your primary side changes with the voltage 360 by root 3, 360 by root 3, 360 by root 3. And already I explained this in the previous slide also. Now the equivalent circuit, because the primary side is delta, so therefore your primary side equivalent parameters will be divided by 3. So it will be 1 by 3 times the original parameter in the single phase transformer, right? So it will become 6.3 ohm, J 7.2 ohm, 2.88 kilo ohm and 2.28 kilo ohm. Whereas your secondary side parameters will remain same because the secondary side is connected in the star fashion, right? It will remain same as it is equal to the single phase transformer, right? And the voltage ratio obviously you know it will change. So for this equivalent circuit, okay. So this is how we represent the three-phase transformer and we go for the analysis of three-phase transformer. Here we can see the transformation ratio for this equivalent circuit is 1.732. Similarly, in this case also it is different, 360 by 120. So for this, the primary side voltage is 360 and the secondary side voltage is 120 by root 3, right? Okay, so here for this equivalent circuit, the transformation ratio will consider here 5.196, right? So this is how we do the three-phase transformer analysis. Maybe in the tomorrow we'll do few more problem on this. Maybe a few more problems on the single phase transformer and three-phase transformer we'll do tomorrow, next class. Okay. Okay, so we'll stop here. Thank you very much. Thanks a lot.